When you are sitting in gridlock traffic staring at that red line on Google Maps, it is natural to assume that there is a sophisticated infrastructure working behind the scenes. You might imagine a network of government-operated cameras on every traffic light, induction loops buried beneath the asphalt, or perhaps real-time satellite imagery monitoring the flow of vehicles. The reality, however, is far less cinematic but technically more impressive. The infrastructure is not in the sky or under the road, it is inside the vehicle. Specifically, it is inside your pocket, and the pockets of the drivers surrounding you. The core technology that powers Google Maps is called Crowdsourced Telemetry. To understand how this works, we must look at the device itself. Whether you are using an Android phone or an iPhone with Google Maps installed, your device acts as a sensor node. When you agree to the terms of service and enable location services, a step most of us do without a second thought, you are effectively opting into this global sensor network. The process is continuous and automated. Your phone periodically sends a data packet to Google servers. This packet contains an anonymous user ID, your precise GPS coordinates, latitude and longitude, and crucially, your current velocity. Google collects this data from billions of devices simultaneously. They are not tracking you as an individual to see where you are going. They are aggregating the data to understand the behavior of the road segment you are on. Here is the logic. If the server receives data from 500 distinct devices on a specific stretch of highway, and the average velocity of those devices is 100 kilometers per hour, the system classifies the traffic flow as free-flowing and paints the line green. However, if those same 500 devices suddenly decelerate to 10 kilometers per hour, the algorithm detects a congestion event and changes the line to red. It is a statistical model based entirely on the collective speed of the users. But relying on raw GPS data presents a massive technical challenge, particularly in modern cities. This is known as the urban canyon effect. GPS technology relies on a line-of-sight connection with satellites orbiting the Earth. In a dense city filled with skyscrapers, these signals cannot travel in a straight line. They bounce. The signal reflects off the glass windows of office buildings and concrete structures before reaching your phone. This phenomenon, called multipath error, delays the signal, causing your phone to miscalculate its position. This is why, when driving in a downtown area, your location dot on the map might appear to drift sideways, hover inside a building, or jump to a parallel street. If Google relied on this raw, noisy data, the traffic map would be incoherent. It would look like cars were driving through shopping malls or floating in rivers. To solve this, Google employs a sophisticated correction algorithm known as snap to road. This software uses probabilistic models, often based on hidden Markov models, to determine the most likely position of the vehicle. The logic is grounded in physical constraints. A car cannot drive through a solid wall, and it cannot instantly jump 50 meters to the left. Therefore, the system analyzes the sequence of your GPS points and forcibly snaps your location to the nearest logical road geometry. It essentially cleans the messy, reflected signals in real time, aligning your device with the digital map database. So the smooth traffic lines you see are not a direct representation of raw data. They are the result of massive computational filtering, turning chaotic signals into a clear picture of the road. Collecting GPS data is only the first step. The raw data is often noisy and lacks context. A device moving slowly does not automatically indicate a traffic jam. It could be a person looking for a parking spot, a mail delivery truck stopping at every house, or simply a driver pulling over to buy a coffee. If Google Maps interpreted every stopped phone as congestion, the entire map would be permanently red. To solve this, Google employs a logic layer based on historical traffic patterns. Over the past decade, Google has built a massive database of average speeds for every road segment at every hour of the week. This creates a baseline. For example, the system knows that on a Monday morning, the baseline speed for a specific highway is 80 kilometers per hour. If real-time data shows 20 kilometers per hour, the deviation is significant, and it triggers a traffic alert. However, if the data shows 20 kilometers per hour on a small residential street, where the baseline is also 20 kilometers per hour, the system ignores it. It filters the data based on expected behavior versus actual behavior. One of the most complex engineering challenges Google faced, particularly in Southeast Asia and Latin America, is the two-wheeler problem. In cities like Bangkok, Jakarta, or Hanoi, motorcycles make up a significant portion of the traffic volume. Motorcycles behave differently from cars. They can lane split or weave between stationary vehicles. In the early days of traffic algorithms, this caused a major data conflict. The system would detect hundreds of devices, motorcycles, moving at 40 kilometers per hour and assume the road was flowing freely. It would paint the road green. Meanwhile, the car drivers on that same road were completely gridlocked, moving at 0 kilometers per hour. The motorcycle data was polluting the car traffic data. To fix this, Google had to retrain their machine learning models. They analyzed the specific movement signatures of different vehicles. A motorcycle accelerates faster than a car and has a distinct lateral movement pattern within a lane. By identifying these specific telemetry signatures, the algorithm can now categorize a device as probable motorcycle and exclude it from the traffic calculation for car drivers. This ensures that the map reflects the reality for the vehicle you are actually driving. Another phenomenon the system must handle is the phantom traffic jam. This occurs when traffic slows down without any physical obstruction, like an accident or construction. It is usually caused by a single driver braking too hard, which forces the car behind to brake, creating a ripple effect or a shock wave that travels backward through the traffic stream. Google's algorithms can identify the mathematical pattern of these shock waves. By analyzing the deceleration rates of sequential vehicles, the system can predict that this is a temporary phantom jam rather than a long-term blockage. Furthermore, to validate these algorithmic assumptions, Google uses active verification. This is why you sometimes see a pop-up asking, "Is there still a slowdown here?" It is a human-in-the-loop system where user feedback is used to confirm or correct the machine's conclusion in real time. The final component of the Google Maps architecture is arguably the most complex: prediction. Knowing where traffic is right now is a matter of data collection. Knowing where traffic will be in 30 minutes requires advanced artificial intelligence. When you request a route, Google Maps provides an estimated time of arrival, ETA. To calculate this, Google does not simply look at current road conditions. It uses graph neural networks, a technology developed in collaboration with DeepMind. The system analyzes the road network not as isolated lines, but as a supersegment, a massive interconnected graph where every road affects every other road. The AI evaluates historical patterns combined with real-time variables. It understands the concept of spillover. For example, if a major accident occurs on a highway, the algorithm calculates the probability that drivers will divert onto specific side streets. It predicts that those side streets, currently green, will turn red in 10 minutes due to the influx of detoured vehicles. This predictive modeling has improved ETA accuracy by up to 50% in complex urban environments like Berlin, Jakarta, and Tokyo. It allows the navigation system to route you around a traffic jam that has not even formed yet. However, because the entire system relies on data inputs rather than physical observation, it is vulnerable to data spoofing. The most significant demonstration of this vulnerability occurred in February 2020, conducted by an artist named Simon Weckert in Berlin. Weckert's experiment was designed to test the system's reliance on aggregate data. He acquired 99 secondhand smartphones. He enabled location services and opened Google Maps navigation on every device. He then placed all 99 phones into a small handcart and walked slowly down a completely empty street. To the Google servers, this cluster of devices represented a high density of users moving in the same direction at a very low velocity, approximately walking speed. The algorithm interpreted this specific pattern as a severe traffic jam involving nearly 100 vehicles. Consequently, the map for that street turned dark red. The impact was immediate and physical. The navigation system, believing the street was gridlocked, began rerouting real-world drivers, taxis, delivery trucks, and commuters away from that street to avoid the non-existent congestion. Weckert had successfully created a virtual traffic jam that altered physical reality. This experiment proved that the algorithm prioritizes data density over visual confirmation. It demonstrated that the system is strictly mathematical. It trusts the numbers more than the eyes. To mitigate such blind spots and vulnerabilities, Google has increasingly integrated data from Waze, which it acquired in 2013. Unlike the passive data collection of Google Maps, Waze relies on active reports from users. Drivers manually report police presence, potholes, accidents, and road closures. This creates a hybrid data model. The passive sensors, or phones, provide the quantitative data on speed and flow, while the active users provide the qualitative data on why the flow has changed. In conclusion, the red line you see on your screen is not a simple observation. It is a statistical probability calculated by a neural network derived from billions of signals, and occasionally, it can still be outsmarted by a handcart.